So welcome everyone. It's a pleasure to introduce Uli Kuchner, who is an astrophysicist, physicist, an artist, and a curator, both publishing in astronomy and transdisciplinary context of art science. So she's based at the University of Nottingham in the UK right now, and she simultaneously got her astrophysicist degree and fine arts paintings at the University of Vienna. The first one in the University of Vienna and the second one at the University of Applied Art in Vienna. She's going to tell us today about the next generation galaxy surveys and how we can navigate the cosmic web with them. So thank you very much, Julie, for accepting our invitation. The floor is yours. And here's the audience.
Hello, that's fantastic to see you. Thank you very much for attending and for your interest and for your invitation. You can hear me okay, I hope, so I can start to speak. Yes. So I am a postdoctoral researcher at the University of Nottingham, and some of you are familiar with the astronomy group there. So first of all, I have to say, I have to give you many greetings from Alfonso Aragon Salamanca, who is one of my mentors there, as is Megan Gray and Fraser Pierce. And I will talk to you about the cosmic web, or the large-scale structure of the universe, and how we are planning to observe galaxy clusters that are connected in this cosmic web with observations. All of this is based on a number of publications here, and I'm privileged to work with some fantastic PhD students that I highlight here. So the large-scale structure environments provide the framework for the formation and the evolution of galaxies. So it is instrumental to understand the cosmic web when we want to understand galaxies. That means the ability to form stars, as well as what morphology the galaxies have, what shape it has. They're all driven in part by the environment. And that's best quantified and qualified by the properties of the cosmic web. So it has therefore become really important to understand what this is that I show you in the background, the cosmic web. So when we understand this, then we can fully understand how the environment couples down to galactic scales. And so I will give you a low-level introduction to the topic. And I want to emphasize that identifying the cosmic web, that's CW, the cosmic web, is challenging. And that's because it's very complex. It has individual structures. It is interconnected. It doesn't have one symmetry. It's intrinsically multiscale. So that means that it has large scales, but also smaller and smaller. You will always see a web and a wide range of densities. And so we have focused on examining the connection of the cosmic web filaments to the nodes, the galaxy clusters. And I will introduce all of that to you because we're especially interested in the topic of preprocessing. And this is how galaxies outside of clusters start to transform and quench. And that is something that was typically assigned to clusters themselves. But we now know that things are happening outside of clusters already. So all of our work helps us to prepare for these galaxy surveys that are all happening now and in the next few years, from the very wide scales to the smaller scales. So our solution to all of these challenges, all of these problems, is to have good simulations and step through everything so we know how to prepare and look for in observations. All right. So we're focusing on the problem that I want to study now, right? Galaxy evolution. And we know that galaxies evolve differently in different environments. And this is a very simplified statement and a simple plot here, but it's really a summary of a very wide topic. So we have very strong empirical evidence that galaxy environment connects to galaxy properties, such as colors or star formation capabilities or morphologies, as you can see in this plot, or dynamics, and that these properties vary systematically between what we used to call, at least, the field and the well-virialized regions of clusters. So here you can see a plot where you have different fractions of different morphological types of galaxies, early type as zero and spiral and irregulars. And here it's plotted against the number density. So in this corner, you have very dense regions, and over here, they are less dense. And you can see that the fraction of early type galaxies of ellipticals increases. So we find more early types in clusters. At the same time, the spirals decrease. So many of you will have seen this and know that this is called the morphology density relation. And it's also seen in colors and star formation rates and masses. So that's a very simple introduction to a more difficult problem. Because how does this happen? So how do the galaxies quench mean they stop forming stars? And how do they become these early type, more elliptical red galaxies? And the very high level view is that there can be quenching due to mass and due to environment, and each of them have different effects attached to that. So there may be AGN that drives this, there may be mergers that drive this, etc. I'm focusing on the environments here. That is listed here. So there's a number of different effects. Maybe they are all connected to one another, that all mean in some way or another that gas is being pushed out or is used up in a galaxy. That means that in the end, galaxies don't have gas left to form new stars and thereby start quenching, which means stop star formation and transform. Okay, and we know for many years now that these different effects happen in different environments. So for example, in a lower density environment, we're more likely to have mergers and accretion from the intracluster or intergalactic medium. In high density environments, we have more of these ramp pressure stripping, like this beautiful example where you see gas being pushed out, or tidal stripping where galaxies are shooting against next to one another and are losing their gas because of that, or strangulation. All of these are terrible terms, unfortunately, meaning that they are kind of choked of the food of the gas. So there, to summarize this, are three broad categories between morphology, environment, and quenching that galaxy evolution obeys, and that is quenched galaxies tend to have early type morphology. Quenched galaxies tend to live in dense or massive environments, and galaxies with early type morphologies are found in these dense environments. But of course, I said it's not that simple. Galaxy evolution is driven by both mass and environment and the ability to accrete new material. And this is all related to one another. So, for example, halos in denser regions are typically more massive, but also they accrete more and they form later. compared to a less dense region. So this is a common first order simplified test, is to just compare galaxies in a field environment, in a low density environment, with a cluster environment at the same mass. So we think in this super simple terms, galaxies fall into a cluster out there, they accrete gas and are forming stars. But when they get closer to this cluster environment, there is no more fresh inflow of gas. So star formation only happens with the gas that is available still in the galaxy. And then that gets used up. And in addition, gas is removed and is stripped. And so in the end, you quench the galaxies first slowly and then fast. So this is an easy way of looking at it. Now we're looking at the more challenging question of what actually happens out there. What happens in the surrounding infall region? And this is where the cosmic web comes in. Trying to stop the simulation. And Anna, we didn't test whether this video starts playing, and it doesn't. So now I have to. So this video is not playing, unfortunately. Great. Right. So this is supposed to be a simulation that shows you how the large-scale structure formation happens. Maybe people have seen this before. So we have some sort of intuition how today's large-scale structure comes to be, where this is at the very early time of the universe, where you see some small density fluctuations, but over time they increase. Let me see if I can start this from here. Yeah, for some reason it wouldn't work. But can you see that still?
Yes.
Yeah, you can see it now moving. Okay, so you can see that the, let's see if I can trick it. No, see, as soon as I start this, it doesn't. Okay. You can see how the higher density regions, which is the red part, is collapsing into denser and denser regions. And the lower dense region, which are the blue areas here, are becoming emptier and emptier and are growing. So these are the voids, and this is filaments that are funneling material into the clusters, which are forming here at the end. So this is now at the current time of the universe, where you have these dense nodes, which are the clusters in the cosmic web that you see here as filaments. So the material is collapsing first into sheets that are then collapsing onto another axis into filaments that are then collapsing into halos. So there is a collective flow of gas and halos, so of baryonic matter that moves from the voids to these so-called walls, which are three-dimensional sheets, which are hard to see in this 2D rendering, that are then moving into a collapsed filament, into the galaxies that are forming in the middle here, and into the clusters finally. Oh, and now it was moving. Okay. So how does all of this influence the galaxy formation and evolution? Well, it does. The cosmic web is the driver and is the environment where galaxies form. So here is a simulation that shows you how the progenitor of a Milky Way-like galaxy evolved. And the cosmic web puts fresh gas into the orbit of the circumgalactic medium, so into what forms a galaxy, and injects the angular momentum. It is therefore impacting dynamically, but also the mass and the way of accretion of the galaxy. So we have these galaxy formations along the filaments, and there's a continuous accretion of gas that is falling into the galaxies. So It affects how resilient a galaxy is, whether disks are formed or reformed by constant accretion of new material. It affects the spins and the alignment of the galaxy. So it is really fundamental for the formation, but also for the evolution of a galaxy. Puts the new fresh gas, and as far as we know, given the thermodynamical state of the gas and the galactic medium, this is only happening with the baryonic matter, not with dark matter, right? Okay, we see this still forming. So here is our Milky Way galaxy in the center there, constantly being fed with new gas that is in blue from this filament. You can see that stars are being formed. You have a secondary galaxy that is kind of moving around and is also affecting it. But all of this is happening inside a filament. And so in this theoretical framework of the cosmic web detachment, we think that filaments are also important to interpret the star formation history. So that if a galaxy then comes into an even larger filament, that it might feel the same kind of processes that I was talking about in the clusters, so that it might feel some ram pressure stripping or some strangulation. Again, I'm sorry about the terrible terminology. We haven't come up with anything better. As it gets accreted into the filament. So maybe even being in a filament is enough to quench the galaxy before it gets accreted into the cluster. So clearly something is happening before the galaxy is accreted to the cluster. And so the cosmic web now, what is this? It is defined by a number of critical points. I already mentioned all these terms before, but these are these topological quantities that are extracted from the cosmic web, that are the peaks, so that's the galaxy clusters. They're the minima, so that's the voids, and then these two-dimensional sheets and the one-dimensional filaments. And they have different densities. So here you can see a plot with density on the x-axis, and you see that the voids are in the lower region of the density. The walls here are a little more dense than these blue dashed curve is where the filaments sit, and the yellow is where the nodes, the clusters are. And that immediately tells us that the filaments are at a wide range of densities. So as I said to you earlier, whether you are born in a dense region or not has implications on how massive you are, how much the ability to accrete gas, and when you form. So filaments impact the assembly and the accretion history of the halo. That's usually discussed in terms of this starvation. And so what does it overall look like, the inventory of the cosmic web? Well, filaments don't actually make up a lot of the volume of the universe because they're so thin, right? They only make up maybe 6% of the volume of the universe. The majority is pretty empty, called voids. But the majority of the mass is in filaments. Almost half of all the mass in our universe is located in filaments. It's really important for if you're interested in galaxy formation and evolution. Only 15% of the mass is actually in the voids, which is the majority of the volume. That's kind of mind-blowing to me. Walls are super important, but they are difficult to observe for various reasons. So we're often glancing over them, but I think this is changing with the next generation surveys. This is a kind of tricky plot, but it tells us that it's very challenging to identify the cosmic web and its structures. So in this experiment, many different codes of identifying the cosmic web were tested on the same simulation. Each line here is a different code. They're all called. They're all listed here. Different cosmic web finders. And the test was, do these different cosmic web finders agree on what a cluster is, a node or not, what a filament is, what these walls or sheets are, and what voids are. And the result is that they only agree with finding voids. Each different filament finder or cosmic web detection finder had a different definition of what a filament is. And what surprises me the most is that actually they don't really agree with what a cluster is. I thought that must be the easiest thing to do. When we see a cluster, we know what it is, but no, they really widely disagree on what a galaxy cluster is and what a filament is. So I just want to say that I showed you mainly a two-dimensional projection, but in reality, please think of the cosmic web as actually a sponge. So here's a three-dimensional rendering of it that you can see is actually more like a sponge with nodes in there that are connected by these sheets. So in here you can see what I mean. There are long, thin walls or sheets that are connecting them. And the tunnels in between, those are the voids. So perhaps it's a better name to say it's a cosmic sponge. But in observations, we don't have the luxury to see it in 3D really, even though spectroscopy will help a lot with that. So in observations, like here is the Euclid Telescope, which is one of the telescopes that I am working towards. It's a visible and near infrared space telescope. We have the ambition to map, the majority of the observed sky with these filament finders or cosmic web extractors. Here are some simulations which we use to test how this works on the very largest scales. That's ongoing work. This image here is created by Katarina Kraljic, but there's a bunch of us that are trying to find methods to extract as best as we can on the largest scales the cosmic web for Euclid Space Telescope. That is starting this summer. So all of a sudden it's happening and it will fly, hopefully launch this July. So as I said earlier, it's a multi-scale problem. So you have a cosmic web on really large scales, but you can see that if you just hold, if you open the shutter and expose long enough, all of these structures will appear. There's filaments on every scale, down to tiny filaments that are feeding the galaxy, down to tiny astronomical units kind of scale filaments. This is a geometry that happens on every scale. It's ubiquitous in the universe. For our purposes, we're looking at the large scale structure and looking at how halos are embedded into these filaments. But obviously, one of the questions that people have asked is, can we measure differences of galaxies inside and outside of filaments, like we've measured the morphology density relation in clusters? And surprisingly, it's not entirely clear. So some surveys report that galaxies near filaments are redder, more massive. They have reduced star formation, just like we saw in the early plot that I showed you in the galaxy morphology relation, density relation. But others find that there's an enhancement of star formation near filaments. So the opposite. They think that there is a rejuvenation as a galaxy is inside a filament. I don't think that this is really contradictory as such, but there are just really not a lot of observations yet in detail to show this. The majority of this is done with simulations. And this is because it's really difficult to find and identify which galaxy is inside a filament and which one isn't. And this will hopefully change very soon. And one of the observations that I'm involved in is looking at the regions around galaxy clusters and identifying the galaxies that are falling in through filaments. So I'm just putting this up here to show you what kind of scales we're now talking about moving forward. It's no longer the very, very large cosmic web, cosmic sponge scales, but we're zooming into a galaxy cluster and having the surrounding region 5R200 or similar to 5-6 virial radii around a cluster. That will be a pretty difficult area to look at because you have thousands of galaxies in here. Some of them will be behind, some of them in front. So in observations, that actually is a pretty challenging problem to solve. How do we identify in this kind of area what galaxies are in what environment? Now, we have been preparing this for the WEAF telescope or WEAF instrument. It's a new instrument at the William Herschel Telescope. We just started the observations. So yesterday was the starting of the science verification. It's very exciting. We had first light in December. We've been preparing for this for years. So I'm really excited to say that it's now happening. So we have used simulations to best get, to identify the cosmic web in something that looks like what's on the right side. I mean, this is SDSS, but to an observer, the world looks, or the universe looks very different than to a simulator on the left. So kind of matching the left side to the right side has been the challenge of the last years of many in our group. How do we identify filaments in a cluster outskirts? We didn't know, so we had to test that. And we asked many questions. Each of them, we found a paper for. There were questions like, can we identify filaments in this area? Can we use velocities to get this in 3D? What are the properties and structures of the filaments? How many galaxies do we expect in each environment? What's the impact of the instrument? What happens to the groups that are around that, galaxy groups? What kind of effect does that have on star formation and the gas content? We're doing all of this for the WEAF survey. Many more questions that we had. I'm not going to talk to you about all of them, but we'll focus on pre-processing in the next minutes. So pre-processing is the integrated effect of a range of these processes, of the physical processes that affect galaxies in the cosmic filaments and in the groups outside of the cluster. So there is lots of evidence that that already starts the transformation before the accretion happens. There are different mechanisms that are happening really close to clusters, a bit further out, what observers often call substructure, or then at the very large scale. So these are sort of different areas that one can look at, and they all have different physics to it. Really near the cluster, is a very turbulent environment. There are shocks, accretion shocks that are surrounding the galaxy cluster. So imagine this is your cluster, and you have things coming out that are backsplashing, and then the shock happening from your accreting gas and halos as well, but this is more relevant for the gas. So it's a very turbulent, shocked area. A galaxy or a halo that is coming in and reaching this boundary, this shock region, loses or is stripped of about 30% of its mass. So this is taken from this paper here. So at the virial radius of a cluster, the galaxy has lost already a lot of the gas mass and a lot of some of the stars as well, but this is mainly gas. Now, this is important to note that the dark matter behaves very differently to gas. So just note that this is mainly important for the gas. So we have this region of infall of low density gas from the voids. You have these shocks that are happening at the boundary to the cluster, but there are also shocks at the boundary to the filaments. So it's a super complex environment, these cluster outskirts. Interestingly, if you go into the galaxy cluster, so say the galaxy that is falling in through a filament into the cluster, maybe they are protected by the environment of the filament. So once you're inside and you have reached into the center of the galaxy cluster through a filament, that's a protecting environment. Out there, as you enter the filament, there is this pre-processing happening. We're only focusing on the things that are happening outside of the cluster for now. So outside of the cluster, as I said, it's very turbulent. You can see here the temperature, for example, and the velocities of the environment around a galaxy cluster. And these other panels are stepping through in higher redshift. So this is earlier in time, redshift 2, and we're going down to redshift 0. So this is the current environment. And this I really like a lot, if you can see it. There is a filament that is coming into the center of the galaxy cluster, and you see that it's darker inside than outside. So that means the temperature in the core of the filament is lower than in the surrounding this core. So it's relatively hot in the poofy outskirts of the filament, but in the spine, in the core of the filament, there is a cold gas flow that might be this enhancement of star formation that some find. Oops. There, this is from observations of the really close environment to us. So Brent Tully and others have collected over many years the cosmic flows data of distances and peculiar velocities of galaxies surrounding us. And you can see the real observed movements of galaxies in our cosmic environment and how they're all moving towards the large groups or clusters, but also along certain trajectories. So I like this to see that there are preferred ways, which are the filaments, but the majority, so the center of the base, the basin, is the group or the cluster, which are in the colorful notes here. Okay, so gas collapses towards the filaments and towards the cluster. And as I said, this is a very shocked environment. So we have seen in our simulations that collectively gas is moving towards the filament, which is shown here on the left side, and then it's all falling into the cluster, and we have this really shocked environment where things are coming out of the cluster and back in this kind of backsplash trajectory. It's not hard to imagine that if you are following this collective movement, that the galaxy is affected by this. And we have seen now this is the velocity of the galaxies as they're falling and collapsing onto the filaments. It's pretty fast. So 300 kilometers per second or so, which is a large kind of movement towards the filament. And inside you have a random motion inside this filament. It's like a velocity dispersion of the filament. All of this, for the observers in the room, make it very challenging to really use the redshift information, because actually these have fingers of God effects. So it's washing out because everything is moving. It's a really, on the small scales, it's turbulent mixing of material, thick perturbed filaments that are feeding the clusters. So we were hopeful to be able to use the spectra and the positions. It's difficult to disentangle. Okay, so I've talked at length at how shocking it is in the environment of a cluster. if we go a little bit further out, we see groups of galaxies. So that is also sometimes called substructure, groups of galaxies. And in the literature, you find that up to maybe half of the cluster galaxies actually come through groups. So a group that is here in red, that's taken again from our simulation, is traveling along the filament into the galaxy cluster and deposits all the galaxies in the cluster itself. So there is a very large debate or ongoing debate on how do you identify a group, and that is not at all solved, to my surprise. So you have many different ways of identifying groups. Even though you might think, well, shouldn't that be easy? They're all coherently moving. It's not that easy. But we do know that the majority of groups are going in through filaments and that they can quench star formation. So we know that massive galaxies are more likely to fall into the clusters as groups or group centrals than lower mass systems. We know that the time spent inside a group before falling into the cluster varies enormously. So maybe the central galaxies have been part of this group for many giga-years, but as you sweep up galaxies going into the cluster, these might only be part of the galaxy group for a short amount of time. So that's not enough then to quench. So it's a very buried collection of galaxies inside a group. And then we do see active stripping inside the group, like we have in some examples down here, but that's relatively rare. So for a typical Milky Way-like galaxy, the inner parts, that cold disk of the Milky Way, they will remain bound to the galaxy, and there will be continuous star formation from this disk. Only the very outskirts of the galaxy might be stripped. So is it enough to be part of a group to be quenched? It can quench it, but not necessarily always. So the assumption that every galaxy that comes into a cluster through a group is automatically pre-processed and quenched, I think that's not entirely the right thing to say. So we asked, what happens to the galaxies in the infalling groups? Do they just shoot through, as that ball indicates? So here's a group coming into a cluster. Does it just come out of the other end as a group? And we found that no, the groups usually do not survive the cluster infall. So groups rarely, just as a whole, come through, punch through on the other end. So that also means that most groups that you see surrounding a cluster fall in for the first time. This is a base diagram. So you have the radius from a group center here versus the velocity. Maybe some of you have seen this before. And every colorful point here denotes one galaxy. And we can see that as this group is falling closer, is falling through a cluster, what happens to the galaxies? First, they get a kick in the, they get a kick in the velocity and then get shot out of the group potential. So they completely dissolve the group and stick inside the cluster. There are very few that actually stay within the cluster, within the group potential. So the majority of the groups are no longer as a whole group, and they are inside the cluster, bound inside. So the overwhelming majority of groups that enter a cluster are doing so for the first time. That's important to know, that if you have a galaxy cluster and you find groups around them, okay, they are in their first infall. That's not necessarily the case for all the galaxies around the cluster. All of the points that you see here in yellow are backsplash galaxies. These are galaxies that have gone into the cluster and orbited out again and are on their second way in. So you have up to 60% of galaxies around a cluster that are have been processed by the cluster themselves. By implication means that if you only look inside a cluster and just outside, you won't have a field and a cluster comparison. You will have galaxies that have been processed by the cluster. I hope that makes sense. So that shows what this backsplash means. So galaxies come into the cluster, fall back out and turn around and fall back in again. So we have a large area around it that are backsplash galaxies that are returning, that are leaving and are returning again. This depends on the dynamical state of the cluster, how far out they go, but that also has many other implications. With semi-analytical models, we saw that if you find a quenched galaxy around a cluster, the likelihood that they have been going through the cluster is very high. So 65% of all the quenched galaxies around a cluster are actually backsplash galaxies. So they have been processed by the cluster. That means that it becomes important to think of the entire evolution, the entire environmental evolution of a galaxy, not just the current environment. In this schematic, I show here's a cluster, here's a filament, and you can see the heterogeneity of what a filament is made of. You have galaxies that are in groups, you have galaxies that have only been in filaments and have been falling onto filament a long time ago. And then you have this rising fraction of backsplash galaxies that look like they've been pre-processed by maybe the filament, but really they've been pre-processed by the cluster. So the summary slide of that is galaxies fall into a cluster, at least, there's probably between 30 and 45% that go into a cluster through filaments, but the filament itself is not a homogeneous environment. It is itself made out of groups, backsplash galaxies and pristine galaxies. That depends on a bunch of things. And we're also preparing a paper now that tells us the probabilities of matching galaxies to environments in observations. Now, what does that mean for gas removal and pre-processing? This is based on semi-analytical models, same simulations, always using the 300 project. And we see that the majority of infallers quench after the first passage, but there is a fraction that needs the second passage to really quench, especially the lower mass galaxies. And in the recent infallers, this is on the right side here, the majority is quenched by pre-processing. But those that have been for a long time in the cluster, ancient infallers, they are quenched by the cluster. So this has been the pre-processing. Near the cluster, you have the accretion shocks. Further out, we have these groups. And then even further, we have the large-scale structure, the filaments that are themselves made out of groups and filaments. This is the picture for the William Herschel Telescope. And in the last few minutes, I'm talking to you just about the science surveys. There are 8 different surveys, but I am part of the Weave Clusters survey. And so we have selected 20 clusters, which we like this, and we have a plan in place to cover them with many multi-object spectrograph pointings. So Weave is a multi-object spectrograph instrument. That means that we have 1,000 filaments in each, 1,000 fibers, each to be placed on a galaxy. And we're covering these 20 galaxy clusters and their surroundings with these pointings of weave. And so we are expecting to get thousands of galaxies per cluster structure to really look at all of these effects that I talked to you about. We've been preparing for years now, I really have to say this, to really make the best decisions to understand how do we get filament galaxies, what does projection effect mean, how can we get around these fingers of God effect that I've been very briefly touching on, and what does it mean to really go through an instrument where, you know, these each of these pointings there, each of these symbols, that's a fiber that we place on a galaxy position in the sky, but the fibers cannot overlap. You know, there are some instrumental, they're not errors, but there are shortcomings that we have to take into account to really step from the simulations to the observations. So it's a multi-level process to get from the perfect dark matter and gas environment to something that we can observe on the sky, including fiber collisions and what that means in terms of observation. We think we're in a really good shape to now start the observations. As I said, they are happening as we speak. This is actually the multi-object spectrograph. I should have been showing you this a moment ago, where each of these is a fiber that is now being placed on a galaxy in the sky. And so we're going to cover these 20 galaxy clusters to observe as best as we can and answer the questions about when and how do galaxies pre-process in galaxy cluster outskirts. I think with that, I'm 45 minutes in, so I would like to thank you so much. I hope I was able to talk to you in a way that you also understand me, and I'm open to any questions that you might have. Thank you.
Thank you very much, Uli, for this super didactical talk. Now we open for questions, first from the audience, and